Hi guys, this is week 4 and we're on to sound waves, and we're going to be talking in several videos here about waves. I'm going to try to keep them less than 5 minutes like normal, and we're going to try to get you guys to be able to do a sound wave project, and then we're going to flip over to light waves, reflection, diffraction, and refraction of light and how that works with mirrors and lenses. And we'll talk about some things that you can do there. But today we're going to start with just waves, and we're going to talk about 4 terms to start with, and then we're going to get into how those combine to make this 5th term down here. So period, frequency, wavelength, and amplitude are the 4 terms that we're going to talk about. Now, this is a spring oscillator, and a spring oscillator behaves just like a wave. So if I push this down, you can see it going back and forth. The key to a wave, the key to simple harmonic motion, which waves travel in, is they travel in a sine wave. They go up and they go down. So if I go like this and just let go of this, you can see it's a repeatable pattern, and there's always this restoring force trying to get the spring or oscillator or string this way back to this nice, neat number where the restoring force just happens over and over again. Now, in real oscillators, you have some deadening, and it won't just keep going forever and ever. Now, we can do it this way, or we can do it this way. You can see this one's got a lot of friction, so we lose a lot of that one. Doesn't work very well. In fact, if I take the weight off of it, it might actually, well, it shoots it right off. So a spring oscillator, a wave, works in simple harmonic motion and works based on these 4 terms. So term number 1 is a period. A period is the amount of time a wave takes to go from one maximum amplitude to the other. So if I had a stopwatch here and I went like this and I got this thing going, let me try to get it going here a little better, and I was timing the time it took to get from here to there and back to here. So from here and then back to that, you can see this would be really hard to do with a stopwatch. But if I could time that one oscillation, we would call that amount of time the period of a wave. If you were on the beach at Lake Michigan, and you could go do your experiment out there if you want, I'm going to explain that later, but you were watching the waves come in and you were timing them from how long they were out till how long they came in, that would be a period. Now, if I take the reciprocal of that, and it would be easier to measure the frequency with this, we call that frequency. Okay, so the reciprocal of a period is a frequency. So if a frequency is, or a period is the time for one oscillation, a frequency is how many oscillations happen in 1 second. So when we're moving fairly fast like that, it'd probably be easier to count how many times it goes up and down in a second than it would be to actually time how long it took to get up, you know, to make one complete oscillation. So that would be frequency. Big important thing is once a wave is released, those 2 things never change. Frequency and period do not change once the wave's out there. That's going to be crucial. The next one is wavelength. And wavelength is, if I was to draw a wave and went from crest to crest or trough to trough, that distance would be called a wavelength. Now, that wavelength is controlled by the medium that the wave is in. So if I'm a certain wavelength and I'm a sound wave going through air and all of a sudden I hit water, my wavelength lengthens a lot. Okay, now this is going to be important. Wavelength is controlled by the medium that you're in. Okay, so, and you have no idea what it's going to do until you actually try it. So when you talk underwater, it sounds like you can't really hear. That's because the wavelengths have been lengthened, and what you normally hear in a wave doesn't happen anymore. It happens way faster, and you're actually hearing the sound way faster. The last term that I want you to know is amplitude. And amplitude there's a rest line. Like right here is the rest line on this. Amplitude is how far it gets stretched out. So when I do that, you can see that the amplitude goes from here to there, from here to there. In this, the amplitude goes from there, whoop, down to the bottom. And I'm just having fun with this thing today. So if I pulled this down to 8 and went up, the amplitude would be from as high as it went to as low as it went. Maximum displacement. When I put these things together, I can actually determine the velocity of a wave. It is wavelength, how long it is. Now this is a half a wavelength, and I'll explain that in the next video, but how long it is compared to how fast or how many times it goes back and forth in a second, and you can obviously see that frequency would be the best way to measure that. And I have this little device right here that's going to help us do that in a minute, okay? So I'm going to be able to read the frequencies. You're not going to be able to see it. What I need you to be able to do is see that line. So in this particular thing, we have period, the time for one oscillation, frequency, how many oscillations happen per time, wavelength, the length of one oscillation from here to here, and then so on, and then the amplitude, how far did I push it? This is the amount of energy in the wave. And then when I put wavelength and frequency together, I get how fast the energy is traveling from one point to the next.